In this video, we're going to talk about the bond energy of covalent bonds. So we talked about lattice energy holding ionic materials together in a solid state, but let's talk about what holds covalent bonds together. So our covalent bond, we thought about radius and we thought about energy, and the idea was if your atoms were reasonably far apart, they were higher in potential, but as they get closer together, their potential begins to drop. The protons and the electrons around them, as they move closer and closer and closer together, opposite atom protons and electrons are able to be attracted to each other, which lowers their potential. But the closer they get, the more the repulsive effects start to kick in. At first, the attractive forces dominate, and so your atoms can get closer and closer, but eventually they get to the closest they can get. After that, they will shoot up in energy as they start to get closer to one another, because effectively at that point, the electrons from each of them are kind of passed mostly. They're on the opposite side, starts to pull them apart. And the repulsive effects become massive in between the nuclei. Get your atoms too close together and they'll push each other away. But there is a fine balance, and there's a minimum. That minimum talks about the internuclear distance, how far apart to maximize the attractiveness and minimize the repulsive forces as they balance with each other. Well, luckily, all this has been calculated at various points in the past, and so experimentally we can determine that. Up here we have our bond energy for a HH bond, so a dihydrogen molecule. To break it, this is a dihydrogen molecule turning into free-floating hydrogen atoms, breaking them apart. Well, for all intents and purposes, all we have to do is shine light at it. What's holding those atoms together is the electrons between them. If we can hit it hard enough to push the electrons apart, make the atoms push apart and spread back out to create independent atoms, well, we can do this by shining light, adding the necessary energy to excite the electrons in a way that pushes them apart from the other atoms. And so you take a sample of gas, you shine a laser at it at low energy, and then if it's a tunable one, you just keep increasing the energy, shorten the wavelength. Eventually, it'll start to break your atoms apart. At that point, whatever wavelength you're at, that's the energy to break your atoms apart. That is the energy of the bond. Different elements have different associated energies. And so if we look at just elemental material, we have our dihydrogen, we have two carbons bonded, we have two oxygens bonded, we have our fluorines, chlorines, bromines, iodines. There are all these single bonds between two identical atoms. And if we look at the energies, they range quite a bit. 432 for hydrogen, 347 kilojoules per mole for carbon, 204 kilojoules per mole for oxygen. Our chlorine, bromine, iodine gives us a good showing. 234 for chlorine, 139 for bromine, 151 for iodine. It goes down as we move down the column of the halides. Fluorine's a little bit of an exception to that. We'll talk about it at another point. But our chlorine to bromine iodine show that as our atoms get bigger, well, they have a bigger distance between them. The more electrons there are, the more they'll be attracted, but also the more electrons to repel each other. Larger atoms just don't get as close, which means they don't sink down as far in their potential well. Chlorine going to bromine, bromine's much bigger. Bromine going to iodine, iodine's much bigger. And we can see that in their bond length. 199, 228, 266. Because the atoms are bigger, the bonds have to be bigger. Because the bonds are bigger, they're not as close to the opposite charges, they're not as attracted. These were for single bonds. If we want to look at multiple bonds, well, if we look at nitrogen, a single bond between nitrogen was 160 kilojoules per mole, but a double bond is 418. And a triple bond is 945. Dinitrogen, as a covalent molecule, actually has a triple bond. It shares more than one electron. For hydrogen, they each only have one electron to share, but other elements have multiple available valence electrons. Your valence electrons are ones that get shared, and there's no reason you can't share multiple with your neighboring atom. The more electrons there are, the more there is to be attracted to. It still balances out at some point for where the optimal distance and energy is, but more electrons provide for more attractive force. Well, these values are effectively telling us that if I have some energy, say I had H2, I could put in this energy and get 2 H atoms. This would be 432 kilojoules per mole. So 432 kilojoules. And let's say we did it twice. I had 2 molecules, so really I show up with 4 H atoms. Well, that would be 2 times the energy. And if I had some dioxygen molecules, well, we could break those apart. We could push them into free-floating atoms. We could get 2 just oxygen atoms. That would take 498 kilojoules to break the bond between them. Well, these atoms could then recombine. I could have a hydrogen and an oxygen and a hydrogen, and they could pull up and compare with each other. In fact, I could have 2 of those. I have 4 hydrogens and 2 oxygens. I could make 2 waters. The free atoms would combine, and when they go down to make my 2 waters, which would really be down below in energy, well, they're going to give off energy. How much? Well, what are they really making? They are producing 4 HO bonds. If we go back up and look for HO, we find that it's 467 kilojoules per mole for each bond. So this would be 4 times 467 kilojoules. For all intents and purposes, we're doing a Hess law. This is a little bit different than we think about Hess law, but what we've really done is we said, hey, H2, 2 of them, break into 4 H atoms. There's a delta H. 1 O2 break into 2 O atoms. There's a delta H. And 4 H atoms plus 2 O atoms become 2 H2O. There's a delta H. Rearrange this, effectively we've said H2, 2 of them, plus O2 goes to 2 H2O. In fact, you can do this for any reaction. If you want to find the delta H for a reaction, by knowing the bond energies to break the atoms apart from the molecules, and then the energies, well, they're just the opposite direction, same energy if you're combining them, we can actually solve for any reaction. We don't even need delta H formation values in this case. We can just approximate it with the bond energies. Well, our first step here was 2 times 432, so that would be 864 kilojoules positive, it went in. Our oxygen here broke apart, just one of it, so plus 498 kilojoules. And we got a bunch of energy back out. 4 times 467. We're going to find that we have to give away 1868 kilojoules. So we put in 864 plus 498, and we lose 1868. So minus that, what we'll find is total difference of minus 506 kilojoules for making 2 waters. So divide this by 2 to find for each 253 kilojoules per mole of H2O. Now, if you actually go and look up the delta H formation for water, there's 2 values. Delta H formation of water gas is negative 241 kilojoules, and for water liquid, negative 285.8 kilojoules. Now we're right in the middle because we really weren't looking at states here. The bond energies in the table above are an average from a lot of different experimented molecules. And so they average a lot of states, and they average a lot of other connections on the molecule. But we've gotten pretty darn close. Using bond energies, we can actually approximate what we expect the delta H for a reaction to be. It's not as good as actually using delta H formations or Hess law equations directly, but it puts you very much in the ballpark. It gets us very close to the expected values. The reason is, just as we saw below, these are the energy to pull the atoms apart, and if the atoms come together, they have to give off that energy. It just comes back to our curve. If our atoms start up here and drop down to make a bond, they'll give off the energy. And if we have to break them to go back up to being free, we have to put exactly that much energy back in. Let's look at bond strength of hydrogen with the halides. These are very simple systems. They all make only one bond, so there's no other complicating factors to get involved here. 1 hydrogen to 1 hydrogen, 1 hydrogen, 1 fluorine, to 1 chlorine, to 1 bromine, to 1 iodine. What we see with the halides here is that as I go from fluorine to chlorine, or chlorine to bromine, or bromine to iodine, the bond gets weaker. I also see that it gets longer. Well, as we go down the column of the halides, it's just a bigger atom. The bigger the atom, the harder it is to make an effective bond. Now, when we think about these, they're all fluorine with 1 bond to hydrogen, chlorine with 1 bond to hydrogen, bromine with 1 bond to hydrogen. A little oversized here to show it off, but they have to be bigger. That hydrogen has its proton and it has its electrons around it, but iodine has their protons and is substantially larger. So as they try to get near each other, well, the hydrogen can sort of overlap, and it sees electrons nearby, but that iodine really doesn't get anywhere near the hydrogen's electrons. Really, the iodine sees its own electrons basically as much. Something like fluorine, though, that's a bit smaller. Well, if that hydrogen pulls up to the fluorine, the distance the fluorine has to go to see those electrons is not as far. Because the radius for fluorine is different than the radius for iodine, the distance to the electrons is less. The less distance, the greater the attractive force. If you ever held 2 magnets near each other, the closer you got them, the stronger they pulled. Small distance changes can be quite large energy changes. And so because the size of the atom goes bigger as we go down the periodic table, the result is that it tends to form longer and weaker bonds. And that's very much what we can see here comparing to hydrogen. We similarly see this as we go between the chlorines, the bromines, and the iodines. They just get bigger and bigger and bigger. Fluorine is an odd one out. This is because it's actually so small. It's only just started to access the p orbitals. Fluorine is the most wanting of electrons of any element in the periodic table. We'll discuss electronegativity in another video, but it wants them the most. It pulls them in really tightly. As a result, by the time you're close enough to be attracted when it's two fluorines, you're also close enough to be really repelled. And so fluorines will get close to each other, as we can see from the bond size, but they don't sink down as much in energy. Effectively, fluorines will get shorter radius, but they won't go as deep in energy as the chlorine would. Once you're past period 2, once you're in the 3rd, 4th, and 5th, you've had enough p orbitals and so on that the effect is greatly diminished. And so we see a reasonable trend between the chlorines, the bromines, and the iodines, because they don't have the complicating factors of fluorine, where it just entered the p orbitals. It's the first shell to have p orbitals, and it's an extremely electronegative element, so it's really pulling those electrons in. So by looking at the bond energies for covalent molecules, we can see several trends that follow along with our size and attractive trends we see in the periodic table. There's a few odd components, but they usually can be explained by oddities in the sizes of the orbitals or the bond length that we would expect for those atoms.